Welcome, everyone, to the fourth day of the Fall 2021 Martin Gardner Celebration of Mind talk series. It's my privilege today to introduce Glen Whitney for this talk. And Glen, most of you in the Gardner community know as the founder of the National Museum of Mathematics, or MoMath, and he is also an editor in Math Horizons.
Thank you so much. And I want to start by just saying I'm amazed and grateful to the organizers of this event for putting together such a great series. It's been a real pleasure to be involved. And I'm honored to be on this slate. And I'm especially honored to be among the 14.3% of the speakers that get to speak on Martin Gardner's birthday. So happy birthday to Martin. Before I get started, I just want to say that all the mathematics that's going to be in the presentation today is joint work with my colleague, Alyssa Kranz. So this is the story I'm going to tell you about, and it's an old story. It goes way back. Here's a great picture of a Mesopotamian column from over 3,000 years ago. Some slightly younger, over 4,000 years ago, sorry. Some slightly younger tiles from a Roman bathhouse in Lincolnshire. What are these showing? Well, obviously, we have a bunch of repeated little shapes that are being used to fill up, an entire ground with a repeating pattern. And these kinds of patterns have stuck with us over the many centuries and millennia. So here's a modern look of these sort of very similar tilings. So these are equilateral triangles. It's not exactly the same shape of triangle we had before. But we get the basic idea that these shapes are fitting together, they're repeating, there's no gaps, there's no overlaps, and they're filling space. So as I said, this is a story with deep roots, and I mean that not just historically, but also linguistically. These stones that were used, the pieces of stone here that were used in these patterns, the Latin term for those was tesserae, and it had a diminutive form, tesselae, so if they're little stones filling up the space, the term was tesselae, and that's why our modern word for these patterns that you see here are regular tessellations. Here, the word regular refers to the fact that we're using regular polygons. So in each of these patterns, the shape has all equal sides and all equal angles. Okay, and so as I said, this is a topic that's been studied now for millennia. So what are the kinds of questions that you ask? Well, the first thing you might notice here is that you see there's some three-sided shapes and some four-sided shapes and some six. Oops, wait, what happened to five? Did I skip five? Well, there's a basic problem. If you take regular pentagons and you're gonna try to tile space with them, well, you need to surround the central spot. So I've tried to do that as snugly as I can here, and now it's pretty clear there's no way that we're going to fit another pentagon into this space. So there is no regular tessellation with pentagons. Nevertheless, if you let enough centuries go by, you start to see something like this, which is from the Mughal Empire in India, and the word jali just means a screen that would go in a window to shade the view. And you might not see the pentagon, so let's take a little close up here. And it's possible that you still might not see the pentagons, but let's just highlight one there for you. So the artisan here used heavier lines to emphasize a doubling of the tiles. So for those of you who saw Doris's wonderful talk earlier today, she talked about ways that it's important when you double up tiles to form a bigger unit. And the artisan art emphasized that here, but the basic repeating unit of this tiling is a pentagon. So what's the story? What's the scoop? Well, the artist here executed a classic mathematical move. Just relax. Mathematicians, they're a relaxed kind of bunch. So if something doesn't work out the way you want, we don't have any tessellations with pentagons, well, ease up on the rules, give yourself more room. So we're going to drop that bit about regular, but we want to have some structure. So will allow our pentagons to be anything that's convex. What does that mean? It means it has no bites taken out of it. So you can see this one's here is nice and convex. All the sort of points point out. And we're not going to allow these kinds of concave. This would be a concave pentagon right here. And it's got a sort of bite out of it. Or equivalently, it's got one of its vertex angles is greater than 180 degrees. So that's out, but that'll be our only rule. And the question now becomes, what kinds of convex pentagons can tessellate? And this now opens ourselves up to, as you can see, just a host of different patterns. So here's a few examples right off the bat. And so that becomes the central question of this story. And following from that comes a very rich mathematical story. As you can see here, it spans over a century of formal work. And of course, the roots go back, as we saw, millennia, but over a century of formal mathematical work. And well, Martin Gardner, very appropriate for this series and for today. Martin Gardner played a central role in the story, as you can see by that one of the headlines of his mathematical games column there. But there's been many other folks involved. Rice here and James were amateur mathematicians, so you get both amateur and professional mathematicians. You see there's a mix of men and women who were involved. Different technologies were used over the years. And I have pictures of everybody here who, I believe everybody here who actually discovered one of these tilings that I could find pictures of. So if anybody has pictures of James or Stein, I would love to get some clues of pictures. So I don't have their pictures, so I substituted the tilings that each of those individuals discovered. And this story has over the years been chronicled in Math Magazine. So you can look back and one of the tilings made the cover there. So as I say, it's a real tapestry that's gone through the ages. And besides all that, there's pretty pictures, all kinds of beautiful pictures here. Here's a nice layout of lots of different pentagonal tilings. And these images were generated by Ed Pegg Jr. His mathpuzzle.com website is absolutely terrific. I recommend it to anybody. So, oh, and the other thing, while I'm thinking of it, so you saw there were some pictures from math.stack exchange. That's a great place if you're mathematically inquisitive and you don't know about it. That's definitely worth a visit. And if you have burning questions about math, that's a great place to try to get them answered. Okay, so that's the story I was going to tell you about. And I'm not going to dive into that story, but I hope I've shown you or given you a taste that it's a great story, and it's a great story for for kind of getting across the beauty of mathematics and the human involvement. And I hope I've also whetted your appetite. To sort of back up the idea this is a good story for talking about math. So that's the story I'm going to tell you about, and it's a setup for the story that I actually want to tell you. And appropriately, because we're honoring not just Martin Gardner, but a number of other mathematicians in this series, this story is, well, as I guess the best way to put it is, it's all John Conway's fault. You see, we had the pleasure of having John visit the museum from time to time early in its history. And one time he was there and he was hanging out in the museum, and he said, I just want to stay here and talk to the visitors and see what they're interested in. It was a wonderful opportunity. And after a little while, he kind of motions me to come over, and I say, yeah, well, what is it? He says, I'm getting tired of just talking. I need to have something for these people to touch and to do something with. And he says, do you happen to have a bunch of squares and matching 1x2 rectangles? And I need one 2x2 rectangle. I said, okay, exactly what pieces do you need? So I wrote it down, and we had a laser cutter. And so real quick, we cut out exactly the pieces that he needed. So I took the pieces over to him. And he said, oh, that's great. I'll try them out. And a few minutes later, he beckons me over and he says, okay, I want you to go up and on the public address system, I want you to announce that John Conway is downstairs with his famous Conway 100 puzzle, and he will give $100 to anybody who solves this puzzle. So, I go upstairs and I make the announcement, and sure enough, a bunch of folks start coming down and they're playing the thing. And then a little while later, he motions over and he says, oh, this is going great. And, they're really dedicated. They're really into it. One of them might actually solve this puzzle. And I said, oh, I broke in that. Oh, that'd be great. imagine like that'll just seal their enthusiasm for math. I beat Conway at his own puzzle. And he says, yeah, can you spot me $100? So anyhow, the moral of that story obviously is you have to give people things to play with. And that's a great way to get them enthusiastic. And so when my colleague and I were invited to give a presentation at a UN conference, a session on encouraging women to be interested in mathematics, naturally we thought of the Pentagon story because of its diverse cast of characters and its long, rich history. But we wanted to actually give them, some pentagons to play with. And it occurred to us that there's so many different patterns there. So like, try to get all those different shaped tiles and fabricate them and get them ready could be a lot. It would be like much more efficient if we had some way of building the tiles. And so we naturally thought of these little pieces here. These are called geosticks. I mean, there's lots of different, basic types of these. And, they stick together pretty intuitively. And we thought like, wouldn't it be great? I mean, there's lots of things you can do with them. Here's a nice, like, this is a pretty good right angle. It's a 3, 4, 5 triangle. And, this is like basically as good as a T-square. And you can even, if you are careful here, you can make some pretty decent linkages out of these. There's a lot of things you can do with these. And I thought, wouldn't it be great if we could like put these together and make some of the pentagons for our tilings? But then that sort of begged another question, which is, these just have the studs at evenly spaced positions along the tile. So any pentagon that we built, sticking these together was going to have all integer sides. And it occurred to us, we didn't even know if the different tiles that we needed to create, if they had integer sides or could have integer sides, or what the story was with that was. So, well, when there's something you don't know, you go and you try to figure it out. So that is where this story takes off. Just to recap, the basic moral of the original story is there are just certain kinds of convex pentagons that tessellate. We already saw that the regular pentagon doesn't tessellate. And we're looking for integer-sided pentagons in those families. And just, so I don't use up all the time saying that phrase over and over again and bore you to pieces, I'm just going to use the word pintegon. This is just for today. This is not a real word, just for today. I'll call them pentagons because I will have to, unfortunately, say that a whole bunch of times. And of course, there's these different families. And so really, this is a search that goes family by family. And I figure it's getting to be the Halloween season. So where better to start than with, and I want to say, what are we doing here? We're doing another classic math move. Maybe mathematicians aren't so relaxed after all. We're going to constrain ourselves. We're going to put this, little handcuffs on. It says now we can only use integers. And I want to just say, by way of showing this is a classic math move, you can see 40 years before us, other folks had a similar idea. They were going to restrict just to the equilateral convex pentagon. So, and it's nice. This is a generalization because, of course, any equilateral convex pentagon, you can scale it down. So all the sides are unit length. So that's a 1, 1, 1, 1, 1 convex pentagon. So that would have integer sides. So they sort of started things off for us. So that's great. And so we knew there would be some out there because of this paper here. Okay. So like I said, it's a Halloween season. So why don't we start off with the creepy, mysterious family 13. And so this will give you a little better idea of what the families are. You can see each one of these families has a certain diagram that shows the constraints. What are the rules that allow membership in this family? So these blue sides have to be the same length, and this one has to be just twice as long. These other colored sides are arbitrary length. And then there's some angle constraints too. These two have to be right angles, and this has got to be 360 degrees minus twice the angle over here. And any convex pentagon that satisfies these conditions, which we can also write out in symbols over here, is in this family, and it's guaranteed to tile the plane. And if it doesn't satisfy these conditions, well, it might be in a different family. It might still tile, but it's not a member of this family. Okay, so we want to begin our search for pentagons. And you can see it's no accident that I've set it up here on coordinate axes, and I've set it up, I've taken advantage of this right angle. So it's going to hit those axes very nicely. And I immediately know the coordinates of this point. It's a comma 0, and this is 0 comma a. And I'm going to do that analytic geometry thing, and I'm going to chase down the coordinates of these other points. And hopefully that'll help us find these pentagons. So let's start with those coordinates. How am I going to get those? Well, I'm going to use my friend, the right triangle here. I've starred one for you. And using the basic rules of trigonometry, if I know this angle, which I do, it's 180 minus this angle here, I can figure out the height of this red segment here, which just happens to be the y coordinate of the point I want. And so the y coordinate there is going to be b sine a. And I can use the adjacent side over here. And of course, I start from a0. So that's where this a comes from. And then it's minus b cosine a because of the law that cosine of 180 minus a is minus cosine of a. Okay, so I've got the coordinates for this point right here. Good progress. Now I've looked for other triangles. There's another one. I've started up here, and I can run that exact same game, and I get those coordinates. And now, so what? So I've got their coordinates. How in the world is that helping me figure out whether these could all be integers? Well, there's another little triangle that is potentially easy to miss, but here it is up here in the corner. And I can chase that one in that same way, and I get this expression for the coordinates of C right here. Well, the real point C, please stand up. There's only one point C. It can only have one set of coordinates. So these two expressions have to be the same. And that gives us a system of equations here. And you can solve that system of equations for cosine A and sine A. And so you get the cosine and sine of this angle right here, just in terms of these side lengths, which, remember, we want those all to be integers. And now you might say, well, so what? Like, what good does it do? It doesn't tell us whether these can be integers. Aha, but the key here now is that it tells us that A is if we want this to be a pentagon, A has to be a very special kind of angle. It has to be an angle where both the cosine and the sine of the angle are rational numbers. You see, if A, B, and C are all whole numbers, then these are just ordinary fractions. And so the cosine and sine of this angle are both rational numbers. And that's a very special thing indeed. And you can show that it only happens when the absolute value of cosine A and the absolute value of sine A are these fractions where A, L, and M are what's called a Pythagorean triple. So they're integers that satisfy the side relation of a right triangle. So the square of the hypotenuse is the sum of the squares of the sides. And if you think about a right triangle, you know that the cosine and the sine are going to be these fractions L over A and M over A. So if this is a Pythagorean triple, so an integer solution to this equation, you get an angle with rational sine and cosine. And the interesting fact that's been known for, I think, hundreds of years, is that that's the only way you can get a rational sine and cosine. So we now know that to get a pentagon, we've got to have a Pythagorean triple. What about the other direction? Which Pythagorean triples are going to give us a pentagon? Well, to answer that, we need to look at the extremes, the boundary conditions of these pentagons. What could happen to this angle A? Well, it could get smaller and smaller and smaller, but when you hit 90 degrees, this stops being a pentagon. It becomes an ordinary quadrilateral, a rectangle. And so that's not going to work, but it can then get bigger and bigger. Everything works in between until you get to, it turns out, 135 degrees. And this is a perfect diagonal here. And once again, it turns into, this time, a trapezoid. So that means the angle A can be anything between 90 and 135 degrees. And the wonderful thing about that is it's tau over 8, 1/8 of a full circle. And if you think about a Pythagorean triple, it was those absolute values. You can have either pair of signs, SIGNs, and you can have either order of L and M. So you get exactly 8 copies for each Pythagorean triple, one in each of those 8-fold slices of the pie. So we have exactly an 8-fold slice of the pie. So we get exactly 1 pentagon from each Pythagorean triple. So we've now demonstrated that the pentagons in family 13 are in 1-to-1 correspondence with the Pythagorean triples, which I think was just, was a surprising fact. It was very pleasant to see an age-old problem link up with this relatively new problem. And so now, using this formula for what the sides are based on your triple, you can there's a procedure where you can list out the Pythagorean triples one by one. We're only interested in the primitive Pythagorean triples. That means the ones that have no common factor, because we could always scale the pentagon up and down by an integer factor. And so these are all of them. We can now list out all of the pentagons in family 13. So that went pretty well. We should attack a different family. But I'll warn you that not all families are alike. If you might think that, okay, now we've got the process, we're just going to chase these right triangles and figure out all the coordinates and see what happens. Actually, things are quite different. We're next going to look at family 7. So what I've done here is I've mocked, I should say, what are the constraints for family 7? There's 4 sides that have to be equal. They're all in blue. There's one that could be different here. And then this angle here has to be a full circle minus twice this one. And this angle here, as tau is the angle measure of a full circle, has to be a full circle minus twice that one. And so like I said, I put all those constraints into this geometry program. Here's an example pentagon. Oh, it could be a pentagon. If we let B, for example, be 10, then this would become a 10, 10, 10, 10, 16 pentagon in this family. But the great thing is I can now drag this point here. That's changing the angle C. And like I said, all the constraints are in here, and it only finds one solution for each of these angles C. So you can see there's just a continuous, what's called in sort of math lingo, a continuous 1-parameter family of solutions to this family 7. And because of that, and you can see well, B is fixed, and we're going to make that to be an integer. And then you can see A just can take on any value in a certain range. So we haven't had to track down any coordinates or anything. A can take anything in a range. So we just need to determine what that range is. And then we'll know the pentagons, because any other integer in that range will be fair game. So over here, it's pretty clear what's happening. We can just make A shrink down and down. It's disappearing, disappearing. It can clearly go down to 0. So any integer less than B will work out. We'll get a pentagon. And so then the question is, what's the other extreme? What's going to happen as we make this bigger and bigger? And we're clearly approaching some kind of limit. You see, we can't go past that point. As soon as we go below the axis and the A disappears there, it's no longer convex, because you see this angle here will get bigger than 180 degrees. And as we mentioned, that means there's now a bite taken out of this. It's not convex. So what does this seem to be heading to as we get there? This number maybe doesn't look particularly familiar, but maybe here, maybe I can help. Well, if instead we display this particular quantity, A over 2B squared. Why would we want to look at that? Well, I've read this script before. If we look at that quantity as we get very close, some of you might recognize what this seems to be heading to. And I wish I could see the chat for any suggestions that you might have, but because of this video setup, I can't. But there you go. if you sort of recognize what's right around that number, and if you guess where this might be going, yes, indeed, that is the golden ratio. So, what's a problem that doesn't have the golden ratio come in, right? It's not really anything. So here it is. There's a cameo appearance of the golden ratio. And so the upshot of this whole story is that, again, and this is like, just follow the pictures, really pleasantly easy just with the pictures. The pentagons in family 7 are exactly those that have sides A, B, 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 B for whole numbers A and B, where A is bigger than 0 and A is less than twice the square root of the golden ratio times B. So another lovely story. Okay, so those are the two broad classes of solutions. But I will warn you, there are some deeper waters here. And looking at my clock, I think we have just enough time. You see, there's this little arrow here inviting us to dive down into these deeper waters. This is family 11. As you can see, it has somewhat more complicated constraints. There's 2 basic distances, A, and there's 2 copies of A here and 2 copies of A here, and then there's C. So these 2 sides, ED and DC, are equal, and they happen to be 2A plus C long. So it's a complicated set of arrangements. That's kind of your first clue that maybe something a little trickier is going to be going on here. So let's go ahead and dive down. All right. So we're going to start the same way as we did with the first family that we looked at, family 13. And we're going to do the coordinate chasing, and you get these somewhat more complicated expressions, 2 different expressions for the point C. So it's the same deal. You chase around this way to get one set of expressions, and you chase around this way to get the other set of expressions. And that will give us this set of equations when we set the coordinates equal to each other. And I've replaced the angle C/2 by gamma, just so I don't have to keep writing those big C/2s. And you can solve the system of equations. For all these, when I say you can solve the system of equations, you have to go and dust off all those, I don't even know, like trig identities, like what is sine 2 gamma, and all the different trig manipulations to do these solutions. And so you can solve that for sine gamma again, but just like before, we don't really care about sine gamma. But you can now substitute that back into the expression for B, and you get this big thing where, to try to make it a little more presentable, I've used the abbreviation that capital H is A squared plus 3D squared. That's what comes out of the geometry of this family. And well, again, where does that leave us for our search for pentagons? Well, B is sort of the only odd distance out here. It's the one that has the only distance that has no constraints on it. So we could just specify A, and in this case D. If you know D, you can figure out what, well, the E is the same, and you can figure out what C is. So you can just specify A and D to be whole numbers. And then the thing you need to know, does B come out to be a whole number? So how could that happen? We have this big complicated expression. How could this come out to be a whole number? Well, I mean, you might get lucky. Maybe H happens to be a perfect square, but maybe it doesn't. Maybe there's other pentagons out there. Well, how could that work? Well, this funny square root here would have to then cancel out the square roots in this other part here. And if you think about it, that means that it would have to, the value of this big square root would have to be an expression, some expression in this square root that didn't involve any other square root. So only involved the square root of H and then some rational numbers. Otherwise, things couldn't cancel out. You couldn't end up back to an integer. So our question then is, and it's going to lead us into a detour into classical number theory. So if H is A squared plus 3D squared, when is that funny square root actually secretly of the form R plus S times the square root of H for rational numbers R and S? And So that's our question. And how are we going to answer a question like that? Well, first we might think about that. Like, suppose square root of h didn't even exist. When is square root of n of the form r for a rational number r? Or just in brief, what natural numbers, what whole numbers have rational square roots? So we can start listing them out. Square root of 1, yep, it's rational. Square root of 2, no, well, it's one of those classic things. It's proved, so it caused the Pythagorean guy to jump off the boat, if legend is true. Is square root of 2 is irrational, I can't deal with it. Square root of 3 is irrational. Square root of 4, no, that's rational, it's 2. Square root of 5 irrational. Square root of 6 irrational. Square root of 7 irrational. Square root of 8 irrational. Square root of 9, another irrational. Another irrational number 3. Wait a second. It seems like only the perfect squares have rational square roots. And that is indeed the case. Among the integers, only the perfect squares have rational square roots. So it turns out that something very similar is true for these funny numbers of this form r plus s times the square root of h. The only way that square root can come out to be rational in the square root of h is when it's a perfect square in these expressions that involve the square root of h. And the only difference from the natural numbers is that these j and k here can be either a whole number or half of an odd number. And this is from work that was done by Dedekind. It dates back into the middle of the 19th century, but don't be fooled. This is really the gateway. This is one of the cornerstones into modern number theory. It's one of the motivating questions that really began the study that has led to so many beautiful results in modern number theory. So it's great to see that coming in here. And so now we can use this. And now I unfortunately don't have time to go into the fine details here. You use this, you say, okay, now I know that this h would have to be, of this form, j plus k square root of h squared. I can put that in, and I can now try to chase this down. And it turns out you arrive at a contradiction. In fact, we can't get these square roots to cancel out in this particular case. Other equations it might work, but this one it doesn't. And so it turns out that this capital H has to be a perfect square of a regular old integer. It's got to be 1 or 4 or 9 or 16 or so on. So we know there's an integer h such that a squared plus 3d squared equals little h squared. And now we can take this big messy formula and we can simplify it a little bit. Now it's got to have these integer h's in it. And we haven't quite squeezed this lemon. We haven't gotten all the juice out of it because, well, this still has to be rational. So we now know that this quantity here has to be a perfect square. And that's not all. Wait, there's more. This number has to be positive, because if this number is negative, then b would be negative, and it's really hard to build a pentagon with a negative side length. So we're going to disallow that. So instead of just one condition that's got to be satisfied with integers, we now need to find 4 integers so that 2 equations and an inequality hold. And then we get a b satisfying all this, and we get a pentagon. And so as you might imagine, with all of those constraints, now again, there's a process. We can adapt the process for Pythagorean triples and find all of the A, D, and H to satisfy this. And then we can sort of filter them out by these other conditions. But so as you might imagine, because of all of that, family 11 pentagons are quite rare finds. In fact, this one here now shown, I filled in the values of all the sides for you. This is the smallest one possible. So, and then just for kicks, here's the second smallest one. So they grow quite rapidly. And needless to say, we didn't go to the presentation with like sticks of length 3,750 and say, here guys, build a pentagon. So that one was out. But we did build some. So we have these little pieces that you saw earlier, and we made these little elbows where they snap together. So we can actually put these pieces together and immediately get, oops, here we go, get one of our pentagons. And these are really designed for going on a desktop, but I made my magic vertical tiling board here. And you can see this fits right in here. And we can now play with the tiling and see that there's looks like other places where it might fit in. Sure enough, here maybe it fits down. Oops, no, that doesn't look good, but it does fit here. And you can actually play with these tessellations. Sadly, that conference never actually occurred. That was going to be happening in late March of 2020. So didn't actually occur, but we've got all the pieces, and we stumbled on this great problem. So what remains? Well, the answer is quite a bit. There's plenty more for you to explore. I've checked off 3 of the boxes. I'll let you know in advance that these most recent 2 families are just too tightly constrained. There's just no way to find a pentagon in either family 14 or 15, but that leaves 10 other possibilities for you to investigate. And I will say the broad categories, I've shown you all the broad categories that come up, but I promise you there are a number of more interesting twists and turns if you want to delve into these. And if you want to see these slides, if you want to go through these slides on your own, you can get to this entire slide deck. It's on the web at studioinfinity.org/pentagons. And good luck in your investigations, either of these cases or in what other directions you take this age-old problem, because I'm sure there's more to explore, as there always is in mathematics.
Thank you, Glenn. That was very cool and very fun. And so you've exhausted 3 of the families, or 5, I guess, because you've shown there's no solutions in the other 2. The 15th case was obviously you couldn't have any. Have you looked at the others at all?
Yes. So there's a paper to appear in Math Magazine. That's why I give a little plug at the beginning. That will have the solutions of all the families. But the backlog, I understand the backlog in Math Magazine is pretty big. So it gives you time.
Yes.
The time to do it before it's unspoiled. Notice I did not put up the table of all the solutions here to give you the opportunity to explore.
I see. Perfect. Who describes these families? I think you did mention that, but you could.
Yeah, so like I said, this is a story that spanned at least a century of formal work. The first reference on my big tapestry slide is a person named Karl Reinhardt. His PhD thesis, habilitation thesis, consisted of determining the 5 families of pentagons that tile the plane. Oops, did he say 5? Well, the next guy on the list is no, that guy. I've got the 8 families that, anyhow, I don't want to tell too much of the story. It's a wonderful story and it's great, but I don't want to be a spoiler for anybody.
Yeah. I have to say here that when that 15th tiling came out, that was so exciting, and I spent literally months working myself to try to close out the set. And my approach was very similar to Rao's, but he beat me to it. So.
Okay.
But it was a lot of fun working in that space.
And it's great because those latest developments, also it just added to the tapestry and the cast of characters. That was a multi-person team that found the 15th, and undergrads were involved. And it shows that mathematics is something that's completely approachable to anybody who's just excited by the questions. Yeah.
And of course, Doris here was involved, and Marjorie Rice, as you mentioned.
Absolutely, yes.
Yeah,
I hope I put her picture prominently enough on the big slide.
Yeah.
Doris is absolutely instrumental in connecting up all the different people on that page.
Okay, so here is a technical question. Is it true that pentagons have a better chance of tiling space than random pentagons, whatever that might mean?
Oh, yeah, that is an interesting question. So first of all, you have to ask if you just give me a list of 5 numbers, is there any pentagon at all that has a pentagon, whether it tiles or not, with those sides? And the answer, of course, is not always, because just like there's a triangle inequality for triangles, there's going to be a pentagon inequality that those numbers are going to have to satisfy. And so I suspect it's going to give you a certain fraction of all 5 tuples of integers right off the bat. It's definitely it's not like a vanishingly small, so like it won't be probability 0, but it's not going to be probability 1 either. So you're going to chuck some that way. Then once you got the 5 numbers, well, I showed you one kind of floppy family where really convexity, there wasn't really any the fact that it was integers didn't really play a role. In fact, that result that I gave for family 7, you could just drop the word integer from that. You now know exactly the side lengths of any pentagon in that family. They're numbers, A, B, forget whether they're integers. So because of those floppy families, if it forms a pentagon at all, in fact, yeah, so I don't want to give away too much, but there are floppy families that are gonna, if you land in something that could make a pentagon, your chances of making a tiling pentagon are quite good.
I think maybe, yeah, it's probably a very tricky question because there's an issue of distribution, right? I mean, you can think of it geometrically instead of numerically and just say, consider the set of all convex pentagons, but how do you pick one of those at random? It's
Right.
an uncountable set and there's no obvious distribution. So
right. So the usual trick would be, if you're just looking at pentagons, you would say, okay, I'm going to allow any side length up to 1,000. And I'll take all of the pentagons where all the side lengths are less than 1,000. And then there's just a finite number of them, and you can figure out which ones are tiling pentagons. And so that gives you a probability for 1,000. You say, okay, now I'm going to go up to 1,000,000. Out of all those, what's the probability? And you can see if that seems to be getting closer and closer to some particular number as you let 1,000 go to 1,000,000, go to 1,000,000,000, and so on. So that would be the approach, and that would be the usual term for what's the probability that a pentagon tiles the plane. And I believe that limit exists, and I believe it's quite large.
there was a question, Scott had a question a while back about how do your sticks constrain the 5 angles?
Yeah, well, as you noticed, we ended up building these little blue elbows. That was the problem because, triangles are rigid, but pentagons are not rigid. So we had to build angles. And you might think, well, we're cheating, but we did arrange them so that the distance from a vertex to one of these attachment points is always either a half a unit or 1.5 units. And since you have 2 attachments on each side, you're adding either 1 or 2 or possibly 3 to the side length. So this is still a pentagon, but yeah, we had to build the elbows because there's otherwise no way to make them rigid. And that pre-gave you the angles. And actually, the great thing about that is if you have a bunch of the pieces, even before you've started to, remember how we talked about, like, you have to get a vertex so you can start seeing, oh, well, that angle combination isn't going to work because I've got a little chunk left at that vertex. So even before you start building the pentagons, you can start testing out, will they tessellate, by seeing if the angles will add up to tau, add up to a full circle.
Thank you, Glenn. That was a really fun excursion, and I can see how it must have been a real delight to hit all of these different areas of mathematics, solving this very natural problem. So congratulations on that, and I look forward to the paper. So thanks, everyone.
Thank you.